Good day, everyone. In this video, we are going to discuss about basic integration of algebraic functions. Let me start my presentation. For the introduction, as previously discussed, the process of anti-differentiation or the integration is just the inverse process of finding the derivatives of functions. We have shown in the previous lesson that a function can have a family of anti-derivatives. In this lesson, we will look at antiderivatives of different types of functions. Particularly, we will find the antiderivatives of polynomial functions, rational functions, and radical functions. Let me present the basic theorems of integration. We have it here: one, two, three, four theorems of integration. For the first theorem, it's stated here that the integration of dx is just equal to x plus c. That's the very basic. And for the second theorem of integration, if n is any real number and n should not be equal to -1, then the integration of x raised to n dx is just equal to x raised to the power of n plus 1 all over n plus 1 plus c. Why is it that n should not be equal to -1? It's all because as you look at the denominator, if n will be equal to -1, it will make our denominator 0. Let's have the third theorem. If a is any constant and f is a function, then the integration of a times f of x dx is just equal to a times the integration of f of x dx. And for theorem number 4, if f and g are functions defined on the same interval, then the integration of the sum and difference of two functions, which are f of x and g of x dx, is just equal to the integration of f of x dx plus minus the integration of g of x dx. In this theorem, it simply stated that integrating the sum and difference of two functions is just equal to the sum and difference of each integration of the function. Now, let's proceed with our illustrative examples. In these examples, we are going to determine the following antiderivatives. We have it here: one, two, seven. Seven examples. For number 1, we have the integration of 3 dx. For number 2, the integration of x raised to the power of 6 dx. For number 3, the integration of 1 over x raised to the power of 6 dx. And for number 4, we have the integration of 4 times the square root of u du. And for number 5, we have the integration of the quantity 12x squared plus 2x quantity dx. And for number 6, the integration of t times the quantity of 2t minus 3 square root of t dt. And for number 7, the integration of x squared plus 1 all over x squared dx. Let's proceed with our solution. Using the integration theorem, okay, we need to take note the four theorems and which theorem are we applying. For number 1, using theorem A and C, we have the integration of 3 dx, which is equal to, look at the constant 3. So we're going to place it here outside the integral symbol, and that's equal to 3 times the integration of dx, which is equal to 3x plus c. Because the integration of dx is just equal to x plus c, right? And that's why we have it there, 3x plus c. And for the second example, using b of the theorem, or theorem number 2, we have the integration of x raised to the power of 6 dx is just equal to x raised to the power of 6 plus 1 all over 6 plus 1 plus c. We need to take note, what of what you are doing in the exponent is what you're going to uh, place also in your denominator, in your overall denominator. And then plus c, which is equal to, as we simplify our numerator, that's the exponent 6 plus 1 is equal to 7. We have there x raised to the power of 7 all over, simplifying 6 plus 1, that is 7. Therefore, for our final answer, we have x raised to the power of 7 all over 7 plus c. Let's have the third example. Using the second theorem, we have the integration of 1 all over x raised to the power of 6 dx is just equal to the integration of x raised to the power of negative 6 dx. If you are asking how it happens, remember the laws of exponent. We apply it here, the laws of exponent, which is equal to x raised to the power of negative 6 plus 1 all over negative 6 plus 1 plus c. And as we simplify that, that's equal to x raised to the power of negative 5 over negative 5 plus c. And we are going to rewrite our function, that is equal to the negative of 1 all over 5x raised to the power of 5 plus c. Therefore, our final answer there is the negative of 1 over 5x raised to the power of 5 plus c. This is our final answer. And for our fourth example, we are using B and C of the theorem, or the second and the third theorem we have presented before. We have the integration of 4 square root of u du is just equal to 4 times the integration of u raised to the power of 1/2 du. Where did I get 1/2? Remember that the square root of u is just equal to u raised to the power of 1/2. And then let us apply the theorem. And that's equal to 4u raised to the power of 1/2 plus 1 all over 1/2 plus 1 plus c. And that's equal to 4u raised to the power of 3/2, because 1/2 plus 1 is equal to 3/2 all over 3/2 plus c. And that's equal to, as we simplify this expression, we have 8u raised to the power of 3 over 2, or 3/2 all over 3 plus c for our final answer. Now let's have the fifth example. In this example, we are using the second, the third, and the fourth theorem. In our function, we have the integration of the quantity 12x squared plus 2x quantity dx. And that's equal to, we need to integrate each one of them. Integrate this one separately with this one. So we have it here. It's equal to 12 times the integration of x squared dx plus 2 times the integration of x dx. After that, we apply now the second theorem. You have it here for the first one. For the first term, we have 12x cubed. Why is it 12x cubed? Because x squared plus 1 should be applied there. So we have it there, cube. And for our denominator, the same with our exponent, 3. So that's over 3 plus 2x squared all over 2. Why is it x squared? Because we have it there x. There is an imaginary exponent 1. Therefore, 1 plus 1, that's squared or 2, all over 2 plus c. And as we simplify our first term and our second term, 12 divided by 3, we have it there 4, and then we remain x cubed plus 2 divided by 2, that's equal to 1, and then we are going to copy their x squared or the remaining expression on our numerator plus c. And for our final answer, for example number 5, we have 4x cubed plus x squared plus c. And for our sixth example, using the second, the third, and the fourth theorem, again, we have the integration of t times the quantity of 2t minus 3 square root of t quantity dt, which is equal to the integration of the quantity 2t squared minus 3t raised to the power of 3 halves quantity dt. What we did there is we distribute the t to our 2t and distribute it to 3 square root of t, and we are going to get this one. After that, we are going to integrate each term. Now we have 2 times the integration of t squared dt minus 3 times the integration of t raised to the power of 3 halves dt, and that's equal to, for the first for the first term, look at here, we have 2t cubed all over 3 minus, for this term, we have 6t raised to the power of 5 over 2 all over 5. And then we have it there plus c. And that is our final answer for the sixth example. And for the seventh example, using A, B, and D, we're using here the first, the second, and the fourth theorem. X squared plus 1 all over x squared dx as our given. This is just equal to the integration of the quantity 1 plus x raised to the power of negative 2 quantity dx. If you're wondering how did I get 1, we are doing here the x squared all over x squared, that's 1. 1 over x squared is equal to x raised to the power of negative 2, and then dx. And that's equal to, we will be integrating each term. You have it there, x, as we integrate 1, that's equal to x, plus x raised to the power of x raised to the power of a negative 2 plus 1 is x raised to the power of negative 1 all over, that is negative 2 plus 1, which is also negative 1, plus c. And as we simplify that, that's equal to x minus 1 over x plus c. That is our final answer for example number 7. And that's it for our detailed solution for the 7 examples I have presented to you. This time, you need to take note for this one. This is a caution. A common mistake in anti-differentiation or integration is distributing the integral sign over a product or a quotient. For as you can see it here below, that the integration of f of x times g of x dx, it is not equal to the integration of f of x dx times the integration of g of x dx. We do not apply that here in integration. If you could remember that in differentiation, we applied, we have their multiplication rule and the division rule, or shall I say the product rule and the quotient rule. Here in integration, we don't have product rule and quotient rule. That's why it is stated here. The same goes with the quotient. The integration of f of x all over g of x dx is not equal to the integration of the numerator and then the integration also of the denominator. That is not equal. So please take note for this one. Now let's proceed to our practice exercise. It is your turn to practice and answer the following given. You are going to integrate the following. We have it here, 1 to 17 examples. You can pause this part of the video and take your time answering the examples. And once you're done, you double check that one using any graph, any calculator. We call it application for calculating in integration. You can search that one. There is an application for that that can give you answers, that can give you answer as you place there the equation of the integration. Okay, and these are the following examples that you are going to practice with. And that ends our discussion. Thank you so much and have a good day.